Hello everyone, I am Bharani, pursuing MSc in Physics at RIE Mysuru. In this session, I'll be discussing about zero-dimensional nanomaterials. In this session, I'll be discussing about the introduction, zero-dimensional nanomaterials, few of its properties, and the synthesis methodologies, few examples with its applications. So now I'll be briefly discussing about nanomaterials. According to ISO, nanomaterials are materials with any external dimension in the nanoscale range. This size range approximates from the range 1 to 100 nanometers. The various examples of nanomaterials include quantum dots, nanoclusters, fullerenes, nanorods, graphene, carbon nanotubes, etc. Have you ever wondered why nanomaterials at the nanoscale have different properties than their bulk? Yes, this is because nanomaterials have small size and due to their high surface area to volume ratio. At the nanoscale, materials can display unique physical, chemical and biological properties that are distinct from their bulk properties. These properties are due to quantum effects, surface effects and confinement of electrons, which further leads to change in its conductivity, strength, optical behavior, etc. Additionally, the ability to modify, manipulate nanomaterials at the atomic as well as molecular level allows the creation for materials which have wide range of applications in medicine, electronics and material science. On based of their dimension, these nanomaterials are classified as zero-dimensional nanomaterials, one-dimensional as well as two-dimensional nanomaterials. So moving on to zero-dimensional nanomaterials, these materials have all the three dimensions within the nanoscale range, that is the range between 1 to 100 nanometers. These materials are also commonly known as nanoparticles with its diameter in the nanometer range. Now, if you carefully observe these first three images, these three images are from a tunneling electron microscope, which is of a mesophorous silica nanoparticles. So I hope you are all aware that tunneling microscope generally gives information about the interior of an object, whereas this fourth image corresponds to an mesophorous silica scanned by a scanning electron microscope, whereas scanning electron microscopes provide information about the exterior surface of the object. So moving on to the properties of zero-dimensional nanomaterials, these materials are amorphous or they can also be crystalline in nature. Colloidal silica is a very good example of amorphous nanoparticles, whereas all synthesized gold nanoparticles are crystalline in nature. And these gold particles are single crystalline in nature. There are also few nanoparticles which are polycrystalline. Few of the nanoparticles, that is zero-dimensional nanomaterials, are either composed of single elements or multi-chemical elements. Now, as discussed, colloidal silica is nothing but silicon dioxide. So, as you can see here, silicon dioxide is composed of both silicon as well as oxygen. So, this is the example of multi-chemical elements. Now, these nanoparticles also exhibit various shapes and forms, which might include fullerenes, clusters, atomic aggregates, etc. They might exist individually or they can be incorporated in a matrix. These nanoparticles can be of metallic, ceramic, or polymeric in nature. Few examples of zero-dimensional nanomaterials are quantum dots, fullerenes, which are also known as buckyballs, like C60 fullerenes are also known as buckyballs, and gold nanoparticles and silica nanoparticles. As you observe here, this image is an tunneling electron microscope image of hollow silica nanomaterials with mesophorous shells. So now I'll be discussing about various methods or various techniques which are used for the synthesis of nanoparticles or zero-dimensional nanomaterials. Here are the few synthesis methods listed below. So the first one is lithography. In lithographic technique, an electron beam or an optical beam is used to pattern or situate a quantum dot on a substrate. So this allows for precise control over the placement and the size of the quantum dots. Moving on to the next one, it is colloidal chemistry. This is a famous method for generation of quantum dots. The colloidal method of quantum dot production generally involves synthesizing of quantum dots in a solution form, and this solution is made using a chemical reaction. So basically in this method, precursor chemicals containing the elements needed for the quantum dots. Like for instance, if you need nanodots or carbon dots, so that particular element will be used in making that particular solution. They are mixed together in a suitable solvent and a controlled condition. Then this solution is heated with the addition of ligands. This will promote the nucleation and growth of the quantum dots. Moving on to the next method, it is epitaxy. So in this method, quantum dots are generated, which involves the growth of quantum dots on the crystal substrate using two types of epitaxy techniques. One is molecular beam epitaxy and the other one is small metal organic chemical vapor deposition. So in molecular beam epitaxy, high purity elemental source. For instance, you need gold. The pure form of gold will be taken. So an high purity elemental source are heated in vacuum chamber to produce molecular or atomic beams of the desired materials. Now these beams will be directed onto a heating substrate, and there a reaction will take place forming thin layers of crystalline material. So by controlling the deposition parameters such as substrate temperature, growth rate, we can precisely control the size, composition and spacing of our nanoparticles. Next, moving on to the wet chemical method. In this technique, materials are dissolved in an aqueous solution under high vapor pressure at elevated temperatures. Usually this temperature is around 200 to 300 degrees Celsius. So these methods listed above are used to prepare quantum dots. The first three methods, lithography, colloidal chemistry like colloidal methods and epitaxy methods, are used for synthesis of quantum dots. The wet chemical method and the arc discharge is used for synthesis of gold nanoparticles, aluminium nanoparticles as well as fullerenes. Okay, so now I'll be discussing about few examples of zero-dimensional nanoparticles in details. To begin with quantum dots. Quantum dots are nothing but a man-made nanoscale crystals. These particles are composed of semiconductor molecules which are inorganic, and these quantum dots, when illuminated with an UV light, they generally emit a strong fluorescent light. And the color, that is the wavelength of this emitted fluorescent light, depends upon the particle size, the size of the quantum dots. I'll be discussing about this later. And if you observe this particular image, this is a tunneling electron microscope image of an cadmium selenide quantum dot. As discussed earlier, UV illumination of quantum dots leads to emission of strong fluorescent light. And the wavelength, that is the color associated with this emitted fluorescent light, always depends upon the particle size of the quantum dot. So the basic principle behind this particular phenomena is quantum confinement. So what do you think quantum confinement is? Here, the confinement of charge carriers, say electrons or holes, within the three-dimensional space of the quantum dots is quantum confinement. And this particular confinement arises due to the nanoscale dimension of the quantum dot, which is typically of the order of a few nanometers. So we also know that generally in quantum mechanics, particles like electrons and holes, and its behavior is always governed by wave functions. So when confined within small volume, when these electrons or holes are confined within the small volume of quantum dot, the wave function of these particles actually becomes quantized, meaning that they can only have discrete energy level. So as you see that this leads to quantization of energy levels in the quantum dot, which is similar to the energy levels of electrons in atom. As a result of this quantum confinement, the energy levels of the electrons and holes in quantum dots are spaced farther apart compared to the bulk material. So this phenomenon leads to a unique optical and electronic properties, which is dependent of the band gap. And the size of the quantum dot is directly influencing its energy level and consequently its optical and electronic behavior. So this fundamental phenomena is the basics of the quantum confinement, and this has a wide range of applications in LEDs, solar cell, and quantum computing. So as you observe here, as the particle size of the quantum dot decreases, we observe that the band gap width increases. As a result, the energy associated with, that is the wavelength associated with the emitted fluorescent light also varies. As you observe here, as the quantum dot size increases, once it is illuminated with the UV light, that is the blue light, it tends to emit a strong fluorescent light. And this color of this emitted fluorescent light depends upon the size of the quantum dot. As discussed previously, as the size of the quantum dot decreases, the energy gap increases. So as energy is inversely proportional to the wavelength of the emitted light decreases as the quantum dot size decreases. That is how you observe different colors in this emitted light. Because smaller the quantum dot size, larger will be the band gap and corresponding colors according to those band gap will be emitted. Talking about the applications of quantum dots. Quantum dots can be targeted to specific organs within the body just by coating the quantum dot structure by a suitable molecule. Because of this phenomenon principle, it is used in tissue imaging in the field of medicine as well as a drug delivery agent, especially for the treatment of cancer, where the medicines are able to reach the target specific place in the body and treated accordingly. Moving on to the optical applications, it includes preparation of LEDs and photovoltaic cell. This image here corresponds to a quantum dot made LED. It is also used as components of solar cells, which is known as grad cell, which is shown here. So this grad cell is made up of quantum dot, and quantum dots are also used for making high sensitive photodetectors. It is also used as fluorescent biological imaging and tagging. So in this particularly, what happens is the photostability of this particular quantum dot allows for a long-term imaging experiments without the need for frequent sample replacement. And in this bioimaging, quantum dots are used to visualize the cellular structure, monitor molecular processes, and also track the biological molecules. So as you see here, biological tagging is done to this rat, and this biological tagging process uh, of this quantum dots is also used for identifying the cancer specific cells, which they are working upon now. Okay, so moving on to the next example of zero-dimensional nanomaterials, which is fullerene. So we are all aware that carbon exists in many number of allotropic forms, among which few are graphene, diamond, and also fullerene. So basically, fullerene is a form of carbon having a spheroidal molecule structure. As you see here, it is of a spherical form, which is usually consisting of an halo cage like structure, which is made up of 60 carbons or more than 60 carbons. The famously known fullerene is Buckminster fullerene, which is made up of 60 carbon atoms. And these fullerenes are chiefly generated by arc discharge method. wherein the arc discharge happens between the carbon electrodes in an inert atmosphere. So as you see here, this is the image of an fullerite, which is a molecular crystal which has fullerene molecules at its lattice nodes. Now moving on to the synthesis and properties of fullerenes. Synthesis of fullerenes are done in two ways. As discussed earlier, it is done due to arc discharge methods of carbon electrodes, which was developed by Germany uh, by the scientists Kraskeimer and Huffman. And the other method was laser vaporization of carbon in an inert atmosphere. Moving on to the properties, it cannot conduct electricity because there will be no movement of electrons available from one molecule to the next. Although it does contain delocalized electrons, the electrons are not capable to move from one C60 fullerene to the next because of the symmetrical nature of C60 fullerene. But still, there is an exception in the case of nanotubes that are capable of conducting electricity along their lengths, and these nanotubes are made up of fullerenes. Moving on to the reactivity, as each carbon atom in the fullerene is sp2 hybridized, they are highly reactive. So they can undergo various chemical reactions such as addition and substitution reaction, making them a versatile material science material in nanotechnology. Talking about the low melting point of fullerenes, due to their weak covalent bonds, they have a very low melting point. Moving on to the hydrophobic nature of fullerene, these fullerenes are hydrophobic, meaning they repel water, which is having a great influence in their behavior in biological and environmental conditions. They also exhibit photophysical properties. As you see here, this is fullerene 60, which is also known as buckyballs, is a common fullerene which is made up of 60 carbon atoms, and it is potentially used for drug delivery due to its hollow cage nature, for treating cancer, AIDS, and various other diseases. So moving on to the next example of zero-dimensional nanomaterials, which are gold nanoparticles. These have a wide variety range application in biosensing area, which is due to their unique physiochemical properties and the ease of with which they are synthesized, and due to their tunable optical properties. These are well known and it has a wide application. As you see here, this is an SEM image, that is the scanning electron microscope image of a gold nanoparticle, which is of the order of 100 nanometers. So, gold nanoparticles have a wide variety range of applications, especially in imaging, the optical imaging, computing, tomography, etc. And they are also used for therapies. Photothermal therapy is one particular specific case of gold nanoparticles where the gold nanoparticles can absorb light, especially in the infrared region. When light is exposed to this gold nanoparticles, they generate heat, and this will lead to localized hypothermia. In the context of cancer treatment, this heating can selectively destroy the cancer cells alone, and this process is known as photothermal therapy. Gold nanoparticles are also used for drug delivery, in delivering the anti-cancer drugs, etc. The functionalizing the surface of these gold nanoparticles allows the targeted drug delivery to specific cancer cells in specific sites, improving the therapeutic efficiency. It is also used for diagnosing. Now, I'll be discussing about the application of aluminium nanoparticles. So, it has an antimicrobial effects and biosensing. So, silver nanoparticles have shown microbial properties due to their ability to interact with the bacterial cell membrane and interfere with the cellular function. Their small size, that is the small size of aluminum nanoparticles, allows for an increased surface area and enhanced interaction with the microorganism. And this interaction with the microorganism can cause cell membrane disruption, DNA damage, and it can inhibit the enzyme which is key in the cellular process of that particular microbes, and thereby it reduces the inflammation and shows antimicrobial effects. It is also used for drug delivery. It is also used in making ceramics. It is also used in the process of catalysis as catalyst. It is also used for biofiltration. Thank you.